We are now going to look at how we estimate parameters of our linear model. So the best estimate of our linear model, which is given by y equals beta 0 plus beta 1 x plus epsilon, is going to be the regression line, that best fit line that we learned about in a previous video, y equals b0 plus b1 x. So in other words, beta 0, which is the true population intercept, is estimated by b0. Beta 1, which is the true population slope, is estimated by b1. And sigma sub epsilon, okay, which is our standard deviation for our linear model, is going to be best estimated by our residual standard deviation, S sub e. Now, a natural question to ask is, how good are these estimates? Okay, and so we're going to focus our attention on how good our estimate is of the slope, because that's the parameter that has the best interpretation for our model. And so we're going to focus on that B1, which estimates our beta 1, which is the slope of the linear relationship. And the standard error of B1 is going to be given by the residual standard deviation divided by the standard deviation of our x values over the square root of n minus 1. Now, I'm not able to tell you exactly where this standard error formula comes from, but what I can do is give you some intuition about why it makes sense. So the standard error depends on three statistics. There is the residual standard deviation, which represents kind of the scatter of the data about the regression line. There is our standard deviation of our x values, which represents the variability of the x data. And then there's n, which is going to represent our sample size. Now, what happens as we vary all three of these statistics? Well, as you decrease residual standard deviation, then you have less variability around that line, and therefore you have less error. So that makes sense why it appears in the numerator of our standard error. But if you increase our variability in x, our x values are actually more spread out, which is going to give us a better estimate of slope. So just drawing a little picture, if you have data that looks like this, sure, you can draw a line around it, and that gives you the best fit line. But if you have data that are more spread out in x, then that gives you a better sense of the trend of that data. So that's why if you increase the x values, the standard deviation of the x values, that will give you a better estimate of the slope. And that's why the S sub x appears in the denominator of this standard error formula. So now if you increase n, then standard error, according to our formula, because it appears in the denominator, decreases. And what that means is we have a more representative sample. Right? So more data should decrease our standard error, and it does in this formula. Now, once you have a notion of standard error, then you can, in fact, define a confidence interval. And we're going to define our confidence intervals in the same way that we did previously. We're going to say we have an estimate of our parameter, B1, that's estimating beta 1. And then we're going to add plus or minus, and we're going to use a t, say t 0.025 for a 95% confidence interval, with the appropriate degrees of freedom. And we're going to use a d-value because we're going to assume that we're in a context that's very much like when we were dealing with comparing means. And so we have a normal distribution of our sample means. In this case, we have a normal distribution around our regression line. And we multiply that t by our standard error of our B1. So this looks a lot like when we had our average of y bar, right? Plus or minus, we had a t value, and then we multiplied that by the standard error of y bar. So it's very, very similar. Now, the degrees of freedom formula is going to be n minus 2. Again, 2 points make a line, so you have no variation when you only have 2 points. So it's only when you have that third point and further that you have any sort of variation. So what I would like to do is find a confidence interval for the slope around the regression line for our global temperature data. So you'll recall that given these summary statistics, that we found that the regression line for the global temperature data was negative 3.371 plus a slope of 0.0104 times x. And we had a residual standard deviation of 0.0928. I'm going to use that information to find out a confidence interval around that slope. So the standard error for B1, my slope, is going to be residual standard deviation over standard deviation of my x's divided by square root of n minus 1. And so it's going to be residual standard deviation of 0.0928 divided by my standard deviation of x's, which is 31.551. And then I'm going to divide that by the square root of my sample size, 66 minus 1. If I put that into a calculator, I'm going to get 0.003647. That looks like a very small number, but remember that our slope is also a small number. So beta, or our 95% confidence interval is going to look like B1 plus or minus my t for 0.025 for my alpha over 2, and then a degrees of freedom of, in this case, 64 times my standard error of B1. Now, the t value for 0.025 and degrees of freedom 60, which is on your chart, ends up being 2.00. So we're going to plug in everything here, and my slope is 0.0104 plus or minus, I'm going to do 2.0 times my standard error of 0.0003647. So I'm going to get a confidence interval of 0.00967 to 0.01113. So we are 95% confident that the slope of our line is between 0.00967 and 0.01113 degrees Celsius per parts per million. In other words, as you increase if you increase CO2 in the atmosphere by 1 part per million, we expect on average that the global temperature will increase 0.00967 to 0.01113 0.13 degrees Celsius, right around that 0.01 degrees Celsius that we saw before with our slope. So we now have a confidence interval, and what that confidence interval shows is that that slope is definitely positive, that there's an increasing trend of global temperature based on CO2 temperature in parts per million. So we want to do the hypothesis test that asks whether that slope is zero. So we're going to do some hypothesis testing, and we're going to consider the null hypothesis. The null hypothesis is going to be mu of y given x does not depend on x. So in other words, what we're saying is that if there's no linear relationship between y and x, then the mean does not depend on x. That the average of our y's given x's does not depend on x. But you'll remember, okay, that mu of y given x is supposed to be beta 0 plus beta 1 x. So if that does not depend on x, what we're really saying is that the slope is 0. So our null hypothesis, the best way to state it for our slope is that the slope is 0. That means there's no relationship between y and x, or at least no linear relationship. Now I'm going to point out that this is absolutely equivalent to the null hypothesis that we had before, which was that the correlation was 0. Okay, these two tests that I'm about to do, they're equivalent. Now, the corresponding t-statistic for a t-test is one that's going to make sense. It's that B1, okay, we're comparing that estimate of slope to 0, and then we're dividing it by standard error. So you'll remember that before we had a t-statistic where we would take our average y, we would subtract off some known mean or some published mean, and then we would divide by the standard error of y bar. Well, here the thing we're going to compare to is going to be 0. What are we comparing? Our estimate of slope, just like we had here, our estimate of the average of y. Okay, and then what do we divide by? Standard error. Okay, so this looks the same as our formula before. And then the degrees of freedom is going to be n minus 2. Now, what I want to point out to you is that this t-statistic is in fact equal to the t-statistic where you got r, or correlation coefficient, times the square root of n minus 2 over 1 minus r squared. So in other words, if you rearrange the terms and the definitions of beta 1 and the standard error, the B1 and the standard error of B1, if you rearrange them, you can get it to come out to this t-statistic that depends instead on the correlation coefficient r. And so that's why this test statistic before had such kind of a screwy formula, because it's really just a rearrangement of something that we understand when we're testing whether the slope is 0. So what I'm going to do is conclude by using a t-test to test the null hypothesis for the global temperature data. So my t-statistic is going to be the slope 0.0104. I'm going to compare it to 0, and then I'm going to divide by the standard error 0.000367. And that ends up equaling 28.52. So in other words, our slope is 28 standard errors away from 0. Okay, that's very highly significant. That tells us that P is definitely less than 0.001 if I look on the chart. Okay, but it's not necessary. I can see it's very highly significant. Okay, and then we can reject our null hypothesis And we can conclude that beta 1, our slope, is definitely not 0.